Today, we run these motors with something called the VFD. Before, we used what was called the contactor. And a contactor starts the motor by simply putting power to it instantly. And so a contactor will cause the motor to just come up to speed abruptly as fast as it possibly can, and then it will, depending on the load, it'll run at this 1740. One of the downsides is that the start can be so abrupt you can break stuff, and the reason is this is why it is the same reason that a Tesla is faster off the line than, say, a Dodge Charger with a 600 horsepower motor. And the reason is that electric motors develop all of their torque at the bottom end when at zero. And an induction motor like this can generate 600% torque at start. So when you have something connected to this, say a belt drive, you often hear the belt squealing when the motor starts for a second, because the motor puts out so much torque and comes up to speed so fast that the belt slip. And if you have it connected to heavy machinery and stuff, it becomes a real problem. We use them to drive pumps all the time, and it will cause a pump to come up to speed so fast that it can bend the shaft in the pump from the offset load. So what's happened now in the past 20 years is we've gone to what's called a VFD, a variable frequency drive, because induction motors are run at a speed close to the frequency of the line. So 60 hertz, and there's two, I should back up a little bit. The number of poles in the motor determines the speed versus frequency. Common motors, 2-pole. This one happens to be a 1740. That's actually a 4-pole motor. A 2-pole motor would be 3,600 RPM. And when you look at the motor, you can't tell that it's the slower speed or the faster speed, because the difference between the two motors is simply how they are connected with the windings inside, whether they've connected the windings to have 2 poles or they've connected it to have 4 poles. They also can connect for 6 poles, which gives you 1,200 RPM, and they can go to 900 RPM, all the way down, some big motors down to 300 RPM by having 20 poles. Okay, so anyway, the modern thing that we've done is we've developed VFD, a variable frequency drive, and what it does is it changes the frequency of the current that the motor is trying to run at. So the variable frequency drive can take the frequency from, say, from literally starting at 0 and work its way up to the full speed that you want. So not only can it bring the motor up to speed at a nice slow, steady rate, it also can determine what the maximum speed is. So I can make this motor, which is 1740, run at half that or a quarter of that. All right, now, so this is what is now dominating pretty much in the industry. It has a big advantage when you get to big motors, because big motors, like you start a 10 horsepower motor, say in this building, you'd blink all the lights because of the sudden current draw. With a VFD on it, you bring it up to speed, nobody even notices you started it. Okay, so the VFDs also have a tremendous amount of programming capability to do all kinds of things, determine how the motor stops, what happens in a power failure. Does the motor, and if the power comes back on right away, does the motor coast down or does it come back up quickly? And all that's programmable. Also, the VFDs can detect the slip in the motor, and they can actually run the motor at synchronous speed, 1800, 3600, by actually running the frequency higher than 60 hertz. And in fact, this particular VFD, this goes up to 900 hertz. All right, so at 60 hertz, with a 2-pole motor, you have 3,600 RPM. At 900 hertz, you have 15 times that speed. So you can run, this drive could explode this motor by running it too fast. But this is how we now get high-speed spindle drives in CNC machines. They run them off of VFD, and the motor is basically, the difference in the motor is it's basically got bearings and physical design to take the higher speeds. But as far as how it works, exactly the same way.